Okay, good afternoon, gang, and welcome back to pre-calc. Today's going to be a really fun day. Not a whole lot of calculation today, but a lot of like thinking about cool concepts. And by the end of the day, you're going to know some stuff that I promise you, well, actually, maybe you knew some of it before, but some special stuff, right? Some special stuff. We're going to meet some cool shit today. I would argue much cooler than any of the stuff we've looked at through the rest of the term. Let me turn on the document camera and we can get moving here because I'm excited to get to this. So this, of course, is MAC 1140. The section number is 009. Pre-calc, and today is the 2nd of November, 2021, which is almost a palindrome, isn't it nice? 11221. There's another one here. We would have a palindromic date. Those are kind of rare. I know everybody wants their exams back. I'm working on them. I will get them done for you as soon as I can. I'm going to make one request. So if you are struggling to decide whether to stay in the course, if you're thinking about dropping, if you're considering withdrawing from the class and need the exam 2 grade to make that decision, send me a Canvas message. So I can move your grade, your thing to the top of the stack. I'm working through the tests. It takes a little while. And if you're in this position where you're like, oh my God, I don't know, and without this exam 2 grade, I can't make the decision whether to stay in the class or drop the class. If the first test was really bad for you, and you're thinking maybe you did better on the second test, and if you did do better on the second test, you're going to stay. If you didn't do better on the second test, you're going to drop. Then please let me know that so I can rush grade your test, right? I'll put it at the top of the stack, and I'll get that in there as soon as I possibly can today. Everybody else, test grades will be on like today or tomorrow, right? So I'm working on it, but since the withdrawal deadline is today, 11/2 is the withdrawal deadline. If you're in this position where you're struggling to decide whether to stay or not, please let me know so I can help you. Also, of course, if you're considering withdrawing, it's a really good idea to have a conversation with me about that anyway, because we can talk about what your options are like and see, you know, where you are with the current material and how likely things could go for you for the remainder of the semester. That's it for that. So today, I want to show you a couple more problems from 4.1 or 4.1 like problems. It's unfortunate. There's a little bit of a weird thing that your textbook does. Their definition of an exponential function is just a teensy bit simpler than other textbooks. And your Calc 1 professors will be assuming that you know how to solve just one slightly more advanced type of problem than your book had. So I couldn't put those problems in the 4.1 homework because the Web of Science stuff all comes from the book. But I want to show you one like that. Then we're going to talk about the number E. And we're going to be getting to the number E by thinking about interest. I know it's not a super exciting topic, but I think here is actually a place where you're gonna have a lot of fun. I'm not gonna make you do a bunch of calculations like Joe borrows $1,000 at 20% compounded hourly, anything crazy like that. But I am gonna talk through that compound interest formula and try to help you understand where it comes from and why it works the way it does and how studying that formula leads to the number E. And then we will do a very brief introduction to logarithms. Logarithms are one of those topics that folks usually, the first time you see it, it doesn't click all the way. So I want to kind of show you the thing a little bit today, give you some time to think about it. And that way, when I show it to you more formally on Thursday, you'll have had it in your brain. And that second time, it's much more likely to click. Okay. So I think that's about it. I am out of coffee and water here, though, so I'm going to grab a little bit of that. I'll be right back. All right. So first, I want to look at a problem that really did show up on your 4.1 homework. I'm going to show you how I kind of think about it. And then I'll use that to show you just a slightly more challenging problem, very similar, which is easy if you approach it the way that I approach the easier problems. So here's a problem which did show up on your 4.1 homework. Find the function f of x equals a to the x graphed below. And then they give us a graph. And my graph looks something like this. All right, looks like all these other exponential graphs we've seen. And they tell us that this is the graph y equals f of x. Maybe the horizontal asymptote is labeled. And yeah, right. So you saw problems like this in your 4.1 homework. And I just want to show you how I think about these. The important fact here is that if the point, what should I call it here? I don't want to use A and B. Let's say if the point C comma D is on the graph of the function f of x, then f of c has to be what? So thinking way back to the start of chapter 2. If I tell you that a certain point is on the graph, then what is f of the first number?
D?
Yeah, exactly, right? The y value of that point is always f of the x value at that point. So this would mean that f of c has to be d. This is the main fact that you need to solve problems of this type. So here, I can say since the point, and here's the big thing. The way I approach these problems when you're looking at exponential functions and you're trying to get the equation from the graph or get the equation from some points, if you have the y-intercept, use that first. Since 0, 1 is on the graph, we know that f of 0 must be equal to 1. And for this particular problem, this isn't going to help us. But when it comes to the slightly more elevated problem that I'm going to show you after this, using this fact or using the y-intercept as sort of the first point to tackle, you'll see will make life much easier. But why doesn't that do anything for us here? Well, f of 0 equals 1 means when I plug 0 in here for x, the result should be equal to 1. In other words, f of 0 is a to the 0. So what this tells me is that a to the 0 is equal to 1. Well, that's great, but no matter what you use for the number a, any possible base for your exponential will satisfy this equation. A to the 0 is always 1. This is just saying 1 equals 1, which doesn't tell us anything new. Right? That doesn't help me find the number a. But it is an important fact. All right, so this point being on the graph didn't really tell me anything. And if you think about it, every function of this form has that same y-intercept. That's not special. You probably noticed that as you work through the homework. If I use the other point, since 2, 9 is on the graph, we know that f of 2 has to be equal to what?
9.
Yeah, exactly the same logic as before. F of 2 has to be equal to 9. Now this is going to do something for me. If I follow the same pattern as above, f of 2, since f of x is supposed to be a to the x, f of 2 is a to the 2, or a squared. So this says a squared is equal to 9. And I can solve that equation for a. How do I solve this equation for a?
Find square root of 9.
Yeah, we can take square roots on both sides, right? I'm trying to get rid of that square, get rid of that power of 2. So if I take square roots on both sides, I'll get, and you have to remember to be careful here, when you take square roots on both sides, you always get a plus and a minus, plus minus square root of 9, which is plus minus 3. So it appears from this work that the number a could be two different things. This function could be 3 to the x, or it could also be parentheses, turn the camera back on here, parentheses negative 3 to the x. And we need to figure out which one. So is a equal to 3, or is a equal to negative 3? The question we need to answer in order to finish up this problem. And I'd like you to maybe take a flip back in your notes to the page with the definition of an exponential function. Remember last time we defined what exponentials are, and there were some restrictions on the number a.
It cannot be a negative.
Very good, right? A has to be positive. So f of x here would be 3 to the x. I'd like to just remind you, this is important. Why do we require a to be greater than 0 for exponential functions? f of x equals a to the x. And so we take, remember that a is greater than 0 for any exponential function with base a. That's how we knew to take positive 3 instead of negative 3. But why? Does anybody remember that?
If you would take -3, then it would be opposite. Like the graph would look different.
That's true. And it's not just like a little bit true, it's like big time true. Not only would the graph look different, it would look very different.
It would be symmetrical to that among the y-axis.
Not quite. So, and this is why I wanted to talk about this. So here's 3 to the x. This is our graph. Here are some other candidates. Now, is this second curve what we would get if we used a as -3? It looks like it, right? But I claim that we would be talking about this thing. So the negative being out front means it's not raised to the power of x, right? This is like this. So this is not what you get by taking a to be -3 here. If you take a to be -3 here, that means we're talking about the purple guy. And holy shit, is he ever weird. I don't remember the terminology I used exactly last time. I think I said something like Desmos shits the bed. It has no hope. That's an accurate statement. In fact, you'll see as I try to like zoom around or do anything here, Desmos panics. It doesn't know what to do. It's in real trouble. And there's a reason for that. If you have a -3 all being raised to the x, what happens when you plug in 1/2 for x?
You have a square root of a negative number, which makes it imaginary.
Right. So the reason I can't even get this to display anymore. Let me see if we give a fresh one. We'll try. It's just angry. There we go. So the reason you're getting all these weird dots is because for some x values, g of x would be defined, right? There are numbers you can plug in here. Like if you plug in 1, you get -3. If you plug in 2, you get +9. If you plug in 3, you get -27. If you plug in 4, you get +81. So for whole numbers, this function is defined. But if you start trying to plug in fractions, like 1/2 or 1/3 works, 1/4 doesn't, 1/5 works, 1/6 doesn't. If you try to plug in any fraction where the denominator is an even number, you're going to be into trouble. If you plug in a whole number that is odd, you're going to get a negative number out. If you plug in a whole number that is even, you're going to get a positive number out. And if you plug in fractions like, I don't know, 2/3, that will be okay because the denominator is odd, so you're not taking a square root of a negative. But if you try to plug in anything where the denominator is even, this function will be undefined. And worse still, what the hell would you get by taking -3 and raising it to the pi? Problems are what you get. You get real serious problems. So that's why the best Desmos can do is give us the dots where the thing is defined. And in that case, you see it jumping back and forth all over the place. And there's lots of gaps where the thing isn't defined at all because there's no hope. So exponential functions always have a positive base because otherwise, first off, the functions are very discontinuous. The graphs are like jumping around all over the place. Also, lots of imaginary outputs. Right, these things are horribly behaved. What would the domain be? The domain is incredibly weird. Very weird domain. Right, like x equals 1/3 is okay, but x equals 1/2 is not, and that sort of thing, right? So we don't want our exponential functions to look like this. We want them to look like this, and even this is fine. But remember, when you see a negative out front like this, that means that you're raising 3 to the x and then multiplying by -1, which is not the same as raising -3 to the x. So we got to take a to be the positive number here, right? Bases for exponentials are always positive because otherwise you run into all these issues. All right, you had problems like this in your homework. The unfortunate thing, one unfortunate thing about the textbook that we're using is the way they define exponential functions. In your college algebra class or high school algebra 2 class, if you saw these, you probably saw a different definition of exponentials, just a tiny bit different. Most books define exponentials as f of x equals some constant c times a to the x. You allow for a constant multiple out front. And first I want to say that this is not a big step. Going from a to the x to c times a to the x is just a little transformation, right? Multiplying on the outside by a constant, that's a vertical stretch or a vertical squish or maybe a vertical flip in the worst case. It's not a big step to go from a to the x to c times a to the x, but most books would define exponential functions as those which can be written this way. Another little note, the number c here is often called the initial value. That will be relevant when you talk about IVPs in Calc 1, and then very relevant when you talk about more differential equations in MAP 2302, differential equations, if you take that. There are problems like the one we just solved that involve functions like these, and they're very similar. And I just want to show you how I attack those problems, because I promise you, your Calc 1 teacher, whomever she or he may be, they will assume that you've seen problems like that. And it's just a weird thing that our textbook doesn't have any. So I'm going to take that last problem and modify it just a tiny bit. Let's say find the function f of x equals c times a to the x, whose graph contains the points let's say 0, 3 and 2, 3/4. All right, so this is just like the last one. Last time you got the points by looking at the graph, and then you plug those points into the function to solve for the constant a. This time I'm just giving you the points. And we could say then graph the function. Then sketch the graph. And problems like this have shown up on my exam, the third exam in this class in the past. So again, I just want to show you these and make sure that you're familiar with them. Can anybody suggest how we could get started?
Plotting the points on the graph?
We could. So here is 0,3. And 2,3/4 is kind of hard to see, but it would be somewhere around here. We can plot those points, that won't hurt. But if I want to find the function, this really isn't enough, right? I'm going to have to do some work like we did on the previous problem where we plugged some information in and then solved for a constant. So remember what I said as we solved the last one. Generally, when you're solving problems like this, you want to start by plugging in the y-intercept, plugging in the point where x is equal to 0. So let me use that same orange fact from the previous page.
We can find c like that, right? If a to the power of 0 gonna be 3, it means c is 3.
Exactly. So since 0,3 is on the graph, we know that f of 0 has to be equal to 3. And then I take this formula for f of x, c times a to the x, and I plug in 0. I know that that thing should be equal to 3, right? In other words, f of 0 is, just like Anna said, c times a to the 0. And I am told that f of 0 is 3. So c times a to the 0 has to be equal to 3. And as in the previous problem, a to the 0, a is a positive constant. So a to the 0 is definitely 1. This says c times 1 is equal to 3. And of course, c times 1, that's just c. So this means that c is equal to 3. Having found c, I can update my formula here. I'm not done yet, but I've got something nicer to work with. I now know that my function isn't just c times a to the x, c is 3. So f of x has to be 3 times a to the x. Now that I have this, I can use the other point to find a. And I'll try to demonstrate to you why it's important to do this guy first. So my next steps, just like the second step of the last problem, since 2,3/4 is on the graph, we know that f of 2 has to be 3/4. And what is f of 2? Here's where this is useful. If I started with this point, then I would say f of 2 is c times a squared. Right, c times a to the 2. But if you don't know what c is, the equation c times a to the 2 equals 3/4 is very hard to solve. But if you already know what c is, then you use this guy and you get 3 times a squared is equal to 3/4. So you see, if you didn't solve for c first, this equation would have two variables in it, c and a, that we would have to try and solve for at the same time, which we cannot do. It is a fact that if you want to solve for, say, 2 variables, then you need 2 equations. If you want to solve for 3 variables, you need 3 equations. So if you just wrote down c times a squared equals 3/4, you cannot solve that on its own. But since we already know what c is, this is an equation that I can solve. And so my next question to you is, how do I solve that equation? What's the first step in solving 3a squared equals 3/4?
We can divide everything by 3.
Very good. So when I divide both sides by 3, the left-hand side becomes a squared. And the right-hand side, I'm going to write this out because I want to force us to confront these fractions. So I've got on the right-hand side now 3/4 divided by 3. And this is kind of ugly. I really want to simplify this. How do I simplify this?
It could be 1/4.
It is, yes, exactly. It's 1/4. I'm not trying to condescend to you or speak down to you. I just know that a lot of people, myself included when I was taking this class, have a bit of a hard time knowing exactly what to do and being confident about it. So I want to give you that confidence now. If you're taking a fraction and dividing it by anything, it's very useful to think of both the top and bottom of the big fraction as being little fractions themselves. I think everybody knows that to divide a fraction by something, you flip and multiply. But what do you flip? Well, 3, the downstairs thing here in the big fraction, remember, is the same as 3/1. So to divide 3/4 by 3, you should think of 3 as the fraction 3/1. And then you leave the top alone and you multiply by the reciprocal of the bottom. So when you see stuff like that, 3/4 all divided by 3, remember, figure out which fraction is the big fraction bar, right? And then think of the top and the bottom as little fractions. Then you leave the top alone and you multiply by the flipped over or reciprocal of the bottom. All right, finally, how do I simplify 3/4 times 1/3? What is 3/4 times 1/3?
3/12.
It is, yep, 3/12 is correct, right? We multiply fractions straight across. 3 times 1 is 3, 4 times 3 is 12. But 3/12 can be simplified also. And you can kind of skip through that step if you realize that this is one fraction whose top is 3 times 1 and whose bottom is 4 times 3. So the factor 3 is a common factor of both the bottom and the top, so it can be canceled. And we never need to write the 3/12. We can just say, okay, that's 1/4. And 3/12 is equal to 1/4, right? You can get there by going through that middle step. But I think like the step from here to here is very nice. We never want to write stuff like this as a decimal. Go from here to here very easily just by remembering the rules for fractions, and then go from here to here very easily by remembering the rules for canceling. And those are the sort of things that we really want you guys coming out of pre-calc comfortable with. I know it's possible to get through college algebra without being comfortable with those, but it's not possible to get through Calc 1. For example, if there were some variables in here, if this is like 3/x divided by 3 or 3/4 divided by y, then you really need these tools because there's no way to write that as a decimal or put that into a calculator. So I want to strongly encourage you guys to take the time to internalize this way of doing things because it will be 100% necessary in Calc 1. All right, that's enough of me preaching. You guys did great. So what we've discovered here is that a squared, I'm just going to write it down, is 1/4. We're almost done. How do I solve this?
Find a square root of both sides.
Yeah, just like when we had a squared equals 9, we took the square root on both sides. If I have a squared equals 1/4, I will take the square root on both sides, and this gives us more occasion to talk about fractions. This will mean a is 1 of plus or minus the square root of 1/4. How do I find the square root of 1/4?
Well, it's 1/2.
It is. So you can take the square root of the top and the square root of the bottom. Right? Square roots are powers. Powers play nice with multiplication and division, meaning like you can distribute powers over division. You can distribute powers over multiplication. You can't do that over addition or subtraction, but with multiplication and division, it works fine. And since the square root is a power, the square root of 1/4 is the same as the square root of 1 over the square root of 4. And the square root of 4 is 2. The square root of 1 is 1. So we get plus or minus 1/2. So it's got to be one of those two. And as before, since a must be positive, we know to take or to use a equals the positive square root 1/2. Otherwise, we run into that same sort of crazy looking graph that we got with -3 to the x. All right, so that's it. So f of x is 3 times 1/2 to the x, like this. And that's the first part of the problem done. We found the function. We also wanted to sketch the graph. So I'd like to ask you, is this going to be a growing exponential or a decaying exponential? Which one of those two basic shapes do we have?
Decaying.
Decaying, right? If the base is smaller than 1, then that's a decaying exponential. And you can also see that from the 2 points we plotted here, right? This curve has to be going down as we go to the right. I'm going to redraw that graph over here a little bigger. We've got some more space. And I'm going to begin just by drawing that general decreasing shape, that decaying exponential. Here's the point 0, 3. And here's your decaying exponential shape. This is your y-intercept. 0, 3. If I wanted to label some other points on this graph, definitely I could label 2, 3/4. That would be fine. That would be like right here. What if I wanted to label the point where x is equal to -1? What would that be?
Straight.
Let's see, so 0, 3 is right here, and it looks to me like this point should be above that. Let's see, what happens if I plug -1 into this one?
76.
Yeah, so this is 3 times 1/2 to the -1. And then based on our rules for exponents, 1/2 to the -1, that's 2. So, oops, sorry, this is 3 times 2, which is 6. Sorry, times 2, which is 6. So this point up here is -1, 6. All right, now we have a nice graph, 3 points labeled. Only other thing I would ask you to do is tell me that asymptote. And there she is. Beautiful, wonderful graph, 10 out of 10. Okay. So this is just, like I said, a slightly more advanced problem than the ones that your book has in section 4.1. And this sort of stuff is something that your Calc 1 professors will 100% assume you know how to do. And because it's not in the textbook, I wanted to take the time to show you here in class. That's all I have to say for section 4.1, the basics of exponential functions. In the real world, though, nobody really messes around with exponential functions like this. The truth is, and you notice this, right, that all the graphs from that previous section look the same. They all either look like this or this flipped over. Some of the points might be different, but that same shape, right? They're all like the same thing. So if you want to think about exponential functions, really, there's only one of them. There's really only one exponential function that matters. And all of the others can be seen as transformations of it. And it's not 2 to the x, or 3 to the x, or 1/2 to the x. It's a different thing raised to the x. And in order to discuss that different thing, I need to take a brief detour and talk about interest. So I'm gonna write a bunch of words on the next page, and I want you to write those words down so that you can go back and think about them. But more importantly, I want you to just kind of think along with me and use your imagination. So this is interest. And the number E. This is section 4.2. We're starting now. So imagine that you are a 16th century banker. You own a bank, but it's like 1540 or something like that. Kind of early pre-Renaissance era, no calculators, no computers, nothing like that. But you're starting to see more sophisticated economies. We're moving away from the sort of serfdom, agrarian thing of the Dark Ages, the 12, 13, 1400s, towards something new, kind of walking, slowly approaching the Industrial Revolution. As a banker, the way you make money is by loaning your money out and charging interest. So you loan money to, and this is where the time kind of comes in. If you're living in a city in the 16th century, there's people moving there, lots of people there. You loan money to lots of people. That's how you make money. In fact, the value of your business is the total amount of money you can expect to get back from all of those loans. There's no stock market at this time. You're not investing that money in some sort of security hedge fund bullshit. You're just loaning out money and waiting for people to pay you back. Now, of course, there is interest. And the type of interest people would have been using at this time would be what's called simple interest. So the profits at your bank come from simple interest. And this is like the kind of interest that you talk about in 4th grade math classes, right? Where you take like the amount of money someone borrowed, you multiply by the interest rate as a percentage, as a decimal, and then you multiply that by the time. So that simple interest is the amount of interest they owe you is equal to the amount of money they borrow, called the principal, times the interest rate times the time, where P is the principal, the amount borrowed, R is the interest rate as a decimal, and T is the time, right? The time that they've had the loan out between when they took the loan out and paid you back. So you, this clever 16th century banker, realize that at any given moment, it's very hard for you to figure out how much your business is worth. Because say Sam borrowed some money from you, you don't know how much you're going to get back on that loan until Sam comes back to pay you. When Sam comes back to pay you, then you say, okay, here's the amount you borrowed, times the interest rate, times the time that has gone by. You got to pay me back the original money plus that. And that works well if you're loaning money to 1 or 2 people and you know exactly when they're going to pay it back. But you're a 16th century banker in a 16th century city, and you loan money to lots of people. So what you would like to do to know the value of your institution, let me first record some of what we just said. In this system, you don't know the value of your business, your bank, until everyone pays back their loans. And that sucks. That's no good, right? Imagine the king comes knocking one day and says, hey, you got to pay your taxes. Your taxes depend on the value of your business. And if you don't know the value of your business until everybody pays you back, you got two choices. You can either make a number up and tell the king, but that number might be too big and then you pay too much tax. It might be too small, then you don't pay enough. Or you can send somebody around town to try and collect all those loans. And inevitably, some of those people aren't going to pay you back. They just don't have the money yet. So what you need is some way to figure out how much your business is worth on any given day without going around and trying to force everybody to pay up on that day. In fact, you would like to know the value of your business every day. So at the end of the day, you calculate how much each person would pay back, would pay you, if they repaid their loans today. And you write that number down as their new balance. So maybe you've got 10 loans out to 10 different people in the community. At the end of business on that day, you use this simple interest formula to see how much they would pay you if they came in to pay back their loan on that day. You take that interest, you add it, or you take that amount, the amount they would have to pay you back on that day, and you write that down as the new amount of money they owe you. This way you know how much your bank is worth at the end of every day. You know, if everybody paid back their loan today, this is how much money you would get back. So that's the value of your business. Then at the end of business the next day, you do the same thing. Using the number from the previous day, as their principal to calculate the interest, to calculate the new interest. For that day. Do you know what you've just done? By deciding to calculate the interest that these people owe you at the end of each day, adding that to their account balance, and then using that as the number to calculate the interest for the next day?
It is exponential function.
It is. Yeah, you just invented compound interest. You do this every day. And you've invented compound interest, specifically daily compounded interest. So that process where at the end of the day, you calculate the interest earned since the last calculation and add that onto the balance, that's called a compounding. right? You're seeing how much interest has accrued since yesterday and adding that onto their balance. That is what the word compounding in this setting means. Compound interest is precisely the scheme we've described, where every so often, doesn't have to be every day, it could be once a month, once a week, once a year, it could be once a day, once an hour, once a minute, once a second, where every so often you calculate the interest that has accrued since the last time you compounded, and you add that onto the balance to be used in the next calculation. That is compound interest.
Is this a continuous compound?
It is not, no, but we're going to get there. So eventually, you realize that the value of each account follows the following formula. Follows the formula. I'll use A of t here for the value of the account equals P, the amount of money originally borrowed, times 1 plus R over N raised to the NT. And in your case, where you're doing this daily, would mean N is 365. So instead of actually doing that calculation at the end of business every day, you can just use this recipe. And you'll notice this has 4 variables in it, right? The original interest formula has 3 variables, P, R, and T. This has the extra variable N. N is the number of compoundings. Per unit of time. And T, the time, is usually measured in years. Right, because that's the time scale over which most people pay back big loans. They don't usually pay them back the next day. They usually pay them back like the next year or something like that. So this is called the compound interest formula. P is the same as it was in the previous thing. It's the principal, it's the original amount you borrow. R is the interest rate, or sometimes called the nominal interest rate, the named interest rate. T is the amount of time that has elapsed since you borrowed that money, all like in the previous guy. The new variable N is the number of compoundings, or the number of check-ins, recalculations, per unit of time. So if you're measuring time in years, then 1 year is 1 unit of time. And if you're compounding every day, like doing that calculation at the end of business every day, then you're compounding 365 times for every 1 unit of time, because there's 365 days in 1 year. I'm not going to require you to memorize this formula. You've probably been required to memorize it in some previous math class. I'm also not going to give you problems like Joe borrows $1,000 at 5% compounded monthly for 10 years. How much does Joe pay back, or any shit like that? I think those problems are boring as hell. And if you don't find them boring, that's awesome. I don't mean to offend, but just plugging into a formula you don't understand is not good. But I do hope that you see what this scheme is. It's using simple interest to calculate how much the interest has earned or accrued over that time period, adding that to the existing balance, and then using that to calculate the interest for the next time period. And as Anna said, this is an exponential function, right? So I've written it here as A of t to emphasize that the variable is t. P, R, and N are usually constants, right? You borrowed some amount of money. That doesn't change over time. You borrowed it at a fixed interest rate. That doesn't change. You're compounding. Your bank is going to do this checking in every so often. That's a fixed constant. The only variable here is t. And since this t is up here in the exponent, this is an exponential function. we're going to do a little bit more imagining now. We're almost through this. So as time goes on, no longer the 15th, 16th century, 17th, 18th century, well, really around the 18th century, financial institutions are getting more and more complex. You have a stock market, and banks trade debt with each other in order to make money. It turns out that, especially with a fiat currency system like we have today in the United States and most of the world, all value comes from debt, or at least most value comes from debt. Some of it comes from new ideas, but pretty much all value comes from debt. And the way banks make money isn't just now by loaning money out and collecting interest on it. They also make money by bundling and selling the debts that they have, that people owe them, to other people. And this is done on the stock market. This is called securities exchange. If you're going to bundle and sell debt, then you need to know what those debts are worth at every minute of the day. It's not sufficient to just check in once per day and see how much each of those loans are worth, because throughout the day, the stock market's going to go up and down, and you're going to want to be trading these bundles of loans to other banks in order to make money. So as time goes on, banks need to know the value of their loans more than once per day. If they want to know the value of the loans every hour, let's say twice, let's say if maybe they update Wall Street twice a day, right? Once at lunchtime and once at closing. If they want to calculate their value, twice per day, then they'd use this same formula, but with n equal to the double of 365, which is what? So that's 730. Right, because this is 2 times 365. If they want to know the value every hour, then you're talking about n equals how many hours are there in a year. Well, there's 365 days times 24 hours. And this one I'm not going to do in my head. $8,760. And in the modern world, if you want it, I'll just keep going here, blah, 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 every minute. Then we're talking about using n equals 365. That's once per day, times 24, that's once per hour, times 60, because there's 60 minutes in an hour. So you take that same number there and you multiply by 60. And you're talking 525,600. And if you want it every second, then n would be that number times 60. Let's do the calculation here, times 60 again. 31,536,000. And the truth is, I don't know if you guys know this, the stock market these days does not involve people making phone calls and trading. Stocks, especially hedge funds, banks, big places that trade, they're traded by bots online. Like you've heard of Twitter bots or Reddit bots, these little computer programs that go around and do stuff automatically. Stocks are now traded by bots. That's how it works. It's one bot farm against another bot farm trading to try and maximize the profit for that day. They don't work every second. They're doing work on the order of like tenths or hundredths of a second, like nanoseconds. If you want to know this value at every moment in time, right? If I want to know the value over smaller and smaller time scales, that means I need to use bigger and bigger numbers for n. If I want to know the value at every moment in time, we need to send n to infinity, whatever that means. And this would be your continuous compounding, where you calculate the interest from one nanosecond to the next nanosecond. And you are always compounding. You are compounding at every moment in time. That means that the number of compoundings per year would be infinity, because there's infinitely many moments in a year, right? Those moments are infinitely short, and there are infinitely many of them. You know, about picoseconds, right? 1/1,000,000th of a picosecond, smaller and smaller and smaller units of time, all the way down to Planck time. We'll stay away from the quantum physics stuff, but that's the idea. So if you want to know the value of your financial institution at any moment in time, you need to use larger and larger and larger values of n. And if you want to know it at every moment in time, you want to send n all the way to infinity. And it turns out that this function behaves nicely as n gets bigger and bigger and bigger. So nicely that we can actually talk about plugging in infinity for n in a way that makes sense. The operations to do that are called limits, and you're going to learn about them in Calc 1. Obviously, I can't do that with you here right now because I would need to spend a few days talking about limits before that, and that's not a part of this class. So what I am going to do is I'm going to make a little table for you where we study this as a function of n rather than a function of t. I'm going to get rid of all the other variables. I'm just going to plug in 1 for all the other variables, and we're going to see what this thing does as n gets bigger and bigger and bigger and bigger. So let's make a little table. I'd say here is to this end, we study a of t equals p times 1 plus r over n to the nt as a function of n. With p equals r equals t equals 1. I plug in 1 for everything else. And then I see what this thing does as n gets bigger and bigger and bigger. And the best tool I have for this at the place we are right now, because algebraically this function is quite complicated as a function of n. There's an n downstairs in here in the part of the base. There's also an n up here in the power. The best thing I can do for you guys at this level is make a table. And when I plug in 1 for p, r, and t, you get this. And I'll go ahead and use those values of n that we talked about. First, let's say if I'm compounding once per year, I just check in once per year and see how much you owe me. That's compounding with n equals 1. If I'm checking in every month, that's n equals 12. Checking in every day, that's n equals 365. Checking in every hour was the next one, right? What was that? That was 8760, 8760. Then every minute was 525,600. Every second, that was 31,536,000. And then we'll try and see what happens as this goes to infinity. And just to keep track, this was yearly, monthly, daily, every hour, sorry, hourly. This was every minute. This was every second. And the bots that trade on Wall Street right now, they're still not happy with every second. They need every millionth of a second. They're working really fast. All right, the first calculation I can do by hand. 1 plus 1 over 1, that's 2. 2 raised to the 1 is 2. So when n is 1, this base is 2. The rest I will use Desmos. 1 plus 1 over 12 raised to the 12, that's the monthly thing, that's 2.61304. Rounding there, 2.61304. Next, I'm going to plug in 365 and see what we get. And I'll round again. I'll round to that same decimal place. So here I get 2.7145, is that 457, right? If I round at that same spot, 457. Okay. So if we're checking in daily, then the base of this function is this number, 2.71457. If I'm checking in every hour, that means I'm using n equals 8,760. That means that base is 2.7181267. 18. I'll give a few more figs here. 1, 2, 6, 7. If I'm checking in every minute, that means I need to plug in 525,600 for n. 525,600. 525,600. Then that number is 2.7182792. And then, so you start to notice some patterns here. The first digit is always a 2. And then when you get to n equals 12, you see that that second digit from 12 to 365 becomes a 7, and then it stays a 7. The third digit is a 1, and that is stable, not changing. The fourth digit here is a 3, and then a 4, and then an 8, and it looks like it might stay an 8. Let's see what we get with this. 31,536,000. 31,536,000. We get 2.7182818. All right, rounding that 7 up to an 8 because the next fig is an 8. And it turns out this number, which we're getting by plugging in this very large number for n, you see these are all getting closer and closer and closer to something. The first digit is fixed at a 2. Once the second digit becomes a 7, it stays a 7. Third digit becomes a 1 and stays a 1. The fourth digit, once it becomes an 8, it stays an 8. The fifth digit, once it becomes a 2, it stays a 2. And this digit, once it becomes an 8, it's going to stay an 8 also. These numbers over here on the right are getting closer and closer to a very special number called E. And the first few decimals of the actual number E, I will write down here. It's 2.71828. Those are the ones that I actually have memorized. 182846. And so what you see is that the numbers in the right column, as n gets larger and larger, are getting closer and closer and closer to this number, which is called E. This is something that actually happened, right? This is literally how this number was discovered through studying compound interest with more and more and more frequent compoundings, which was made necessary by the evolution of financial institutions. The whole function, if you study the whole function, a of t, which again was p times 1 plus r over n raised to the power of nt, if you study this as n goes to infinity, the p out front is going to stay there. We call this thing c of t, c for continuous, right? This is where continuously compounded interest comes from. You are compounding at like every moment in time, right? When n is 31 million, whatever, you're compounding every second. When n is infinity, you are compounding at every moment in time. The p out front stays out front, of course, right? He doesn't have anything to do with this piece, he's just multiplying it. The t in the power is going to stay in the power, and the 1 plus 1 over n to the n is going to go to e. The part that's kind of hard to explain is that the r here also shows up in the power. And if we were in calculus class, I would tell you exactly why that is, using something called L'Hopital's rule, but we're not. So I just need you to trust me on this one. And this happens as n goes to infinity. This is regular compound interest. And this is called continuously compounded interest. And again, I'm not going to give you those stupid problems like Joe invests this much dollars at this much interest rate over this much time. How much does he owe? The only reason we're going through this exercise is to introduce the number E and to show you where it came from and give you some historical background. The number E has some pretty important features. First, it is a transcendental irrational number. Now remember, irrational means cannot be written as a fraction made up of whole numbers. So there is no way to write E as a nice fraction. And that's equivalent to saying that the decimal representation goes on and on and on and on and on without any repeating patterns. This does appear to have some patterns like 1828, 1828, but then that breaks. It has a few names. It's sometimes called the natural base. So we're going to use it as the base of the exponential function. When I said that there's like all these exponentials are really pretty much the same, and that there's only one that anybody really cares about, that one is e to the x. Because f of x equals e to the x is the, quote, natural exponential. The reason this is the exponential function that everybody likes is because it behaves really nicely with respect to calculus operations, specifically the derivative and the integral. Obviously, we don't know what those are yet, but this is a fixed point of the differential operator ddx. And for that reason, we call it the natural exponential. It's everybody's favorite exponential because it's the easiest one to do calculus with. It also shows up a lot in the real world, not just in this setting of compound interest, but you can imagine other places where that sort of thing that happens with compound interest happens, like population growth, where the amount of new things in that population comes from the amount of things in that population from the previous day, right? That sort of behavior leads to the natural exponential function in the same way that the compound interest formula does. One of the reasons people call this number E is because of the man named Leonhard Euler. So another name for this is Euler's number. Leonhard Euler is probably the most important man to ever live, or at least the most important mathematician. Euler is on the Swiss franc, the money in Switzerland, or at least prior to the euro. I don't know if Switzerland still uses the franc or the euro. I think they're stubbornly independent, but I think they're on the euro now. He's on the currency for a number of different countries. That's how important he is. In America, you don't see mathematicians on the money ever, but in plenty of other places, specifically in Switzerland, Euler was on the bill. I think the 10 franc mark. Yeah, the 10 franc mark. When you see pictures of Euler, he lived, by the way, around the 1700s. In fact, the same year as the American Revolution, 1776, Euler went blind. And so you always see him squinting like this. So he went blind in 1776 and spent the rest of his life basically laying down and dictating mathematics. He was totally blind. So he wasn't writing anything down or anything like that. He would speak and other people would write it down. And even in that form, completely blind, unable to write and see what he's writing, the man just sat there and dictated mathematical truth after mathematical truth, theorem after theorem, all from his mind. One of the most, if not the absolute most prolific mathematician to ever live. And you see here an equation for which he is quite famous. E raised to the power of I times pi plus 1 equals 0. Now, this is some shocking shit. First off, I here is the imaginary number. So what does it mean to take this weird irrational number and raise it to the power of I times this other weird irrational number? That's very hard to describe. It'll be something I can tell you about after you take Calc 2, but you need power series. There's also this really intense connection, for those of you taking trigonometry, between the number E and the cosine function and the sine function, all having to do with complex numbers. So Euler, epic, just epic dude. Totally deserves to be on money. I wish we had him on some bills here in the United States. And often E is called Euler's number for the obvious reason his name starts with E. I heard recently that that's not true, Euler was just the first guy to use the symbol E for this. I don't know why, and that other people started doing it, but whatever the case, we call this number E. It's a special transcendental irrational number. It is the base of the function e to the x, which is everybody's favorite exponential function. And everybody should love Euler. There's a famous quote, Dirichlet, I think maybe, said, read Euler, read Euler, read Euler. He is the master of us all. And this is coming from a guy who's working in quantum physics hundreds of years after Euler died. It's really true. If you are ever curious about what a genuine mathematical genius's thoughts look like, read Euler, read Euler. He is the master of us all. I'd like to sketch for you the graph of e to the x. It's not a surprising graph. It looks exactly like all the other exponential graphs, but I want to show you and give us some occasion to talk about powers of e. And then I know we've gone over a little bit, and if you have to go after I draw this graph, I understand, but if you can hang around, I do want to motivate logarithms for you briefly. All right, so the graph of e to the x No surprises here. It looks like every other growing exponential in the world. Remember, E is a little bigger than 2.7. It's like 2.71, blah, 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 blah. So this is a growing exponential function. It has this horizontal asymptote, y equals 0, that it approaches on the left. E to the 0 is 1, just like any other number to the 0 is 1. So this point right here is 0, 1. When x is equal to 1, you get out E. So this point right here is 1, E. And the next point over here would be 2, E squared. Maybe I'll try to squeeze it in there. So it's right here. Really, E squared should be pretty close to 9, right? Because E is pretty close to 3. On the other side, when x is -1, you have the point -1, 1 over E, or E to the -1. And the reason, one of the reasons I'm labeling these explicitly is to say, when you see powers of E, leave them as powers of E. Don't write them as decimals. I don't want the decimal. I want you to just say, this is E squared, not 8.9735, whatever. So please leave powers of E as powers of E. Trust me, that's the nice way to work with them. Much, much nicer to say 1 over E than whatever the decimal representation is. There are lots of other exponentials that you can get from this. For example, if I ask you to sketch y equals e to the -x, this is a transformed version of e to the x. What's the transformation? Well, we've replaced x by -x. We've multiplied on the inside by -1. So this would be a horizontally reflected version of that same graph. So here would be 0, 1. Over here would be -1, e. Over here would be -2, e squared. And over here would be 1, 1 over e. And your homework this week is going to have stuff like this, right? Where you have to take e to the x and move it around, flip it over, shift it up and down, all that stuff. All the regular transformation moves. The domain and range are the same as for any other exponential, right? Domain is all real numbers, range is 0 to infinity. Until you start shifting it up or down, then the range will change. There's nothing super special about this graph from the perspective of a pre-calculus student. But from the perspective of a calculus student, there's something very special about this graph, and it has to do with slopes. I won't go into that now because you'll learn it in Calc 1. I don't want to spoil it. Okay, that's it for natural exponentials. That's section 4.2. If you have the time to hang out, I do want to motivate a little bit the study of the logarithm, because this is something that a lot of folks struggle with. If you have to leave, please just watch this later. This is a very brief intro to logs. Next time, on Thursday, we will do a much more thorough discussion of logarithms with lots of formal definitions and algebra properties and graphs. But here, I just want to get your brain ready. So, question. Can we solve the equation 2 to the x equals 3? And you start thinking about the algebra tools that we have so far, like taking square roots or squaring both sides or factoring, stuff like that. None of it will help here. none of the algebra operations we know, or none of the algebra we've discussed, will get that x down out of the exponent. That's a challenge. Algebraically, it's a very serious challenge. And we're going to need to invent a new tool for it. So you might ask yourself, does a solution exist? If I can't solve it, maybe it can't be solved. Reasonable question to ask. The natural way to check this is to look at the graph. If I look at the graph, y equals 2 to the x, it's a growing exponential. This is 0, 1. This is 1, 2. This is 2, 4. So right here is 3. So this is the graph y equals 2 to the x. Let me add in the line y equals 3. So is there a solution to the equation 2 to the x equals 3 from this graph? Can you tell me yes or no?
Yes.
Yes.
Yeah, because the graphs touch, right? Right here. So because these graphs do intersect, there is a solution, and it's this x value. Now, finding that solution, that's another matter. I claim that the solution here is about 1.5-ish, and more specifically like 1.58496. Ish. Something about like that. And we can check. If I raise 2 to the 1.58496, what do we get out? Check that out, 2.999994799. This is incredibly close to 3. So the obvious question is, so how did I find this solution? Approximately. What is the exact solution? How would we find that? It turns out to be all about the inverse function. F inverse of x to the original function f of x equals 2 to the x. That inverse function is called a logarithm, And next time, I'm going to start teaching you all about logarithms. The very last thing I want to do here is give you a quick sketch of the graph of this inverse function, because we can get that without doing any calculation, just from the graph of the original. 2 to the x, remember, looks like this. The point 0, 1 is on the graph. The point 1, 2 is on the graph. The point 2, 4 is on the graph. The point -1, 1/2 is on the graph. Point -2, 1/4 is on the graph. Here's 2 to the x. And if you want his inverse function, remember, you need to flip all the x's and y's in those points over. You need to swap all the x's with y's, which is equivalent to reflecting the whole graph over this line y equals x. So in black here, you have 2 to the x. In purple here, you're going to have the inverse function. Okay, let me go 1, 2, 3, 4. So if 2, 4 is on the original, then 4, 2 is on the inverse. If 1, 2 is on the original, then 2, 1 is on the inverse. If 0, 1 is on the original, then 1, 0 is on the inverse. If -1, 1/2 is on the original, then 1/2 -1 is on the inverse. And if -2, 1/4 is on the original, then 1/4, -2 is on the inverse. And that horizontal asymptote for the original will become a vertical asymptote for the inverse. So here it is, this mysterious inverse to the function 2 to the x. And it's called a logarithm. And it's going to be the key to solving equations like 2 to the x equals 3, and many, many other equations. Exponentials, very, very nice functions. Their domain is all real numbers. They play really well with algebra. There's nothing you can kind of do to piss off an exponential. Logarithms are a little bit more temperamental. Their domain is the range of the exponential. So that domain is just 0 to infinity. Their range is all real numbers, which is nice. And they have some glorious algebra properties. Each one of those rules for exponents that we discussed at the start of chapter 4 last week, there's a corresponding rule for logarithms. It's going to take some practice for you to get comfy with these purple functions. So the most helpful thing you could do between now and Thursday, besides obviously doing the homework, or at least working on the homework a little bit, is to take a look back at section 2.8 in the textbook when we talked about inverse functions. Because again, we're going to be defining these new functions as the inverses to exponentials. And that's where I'll leave it for today. I hope you guys enjoy this. Thank you for sticking around. I really appreciate that sort of patience. If you need anything from me, remember you can send me a Canvas message or talk to me in Discord, wherever. That's it. I'll see you guys next time.